Okay, for the test, there's going to be 10 problems. You can see why as you try to work through these problems. They take a little bit of time. As normal, one sheet of paper, the 8.5 inch by 11 inch version, and both sides is fine. And don't forget your table of integrals. There may or may not, I don't remember what integrals, they may be just simple substitution integration. Some of them may get a little more difficult, so make sure you have your table of integrals in case there's something that's not real straightforward. We have been pushing pretty hard this last couple of weeks, so I will allow you to take the test in the testing center either tomorrow or very last day would be Monday after spring break.
Monday after spring break?
Monday after spring break. Monday, that's March 20th. Now, I did check with the testing center. They will be open next week during spring break. So if any of you are around and want to take it, they're open Monday through Thursday. Friday, the campus is closed. So Monday through Thursday. Definitely make sure you set an appointment ahead of time to make sure they're there. With spring break, it's going to be a little not absolutely for sure that they're there all the time, but I will allow you to do that. If you want to take it tomorrow, that's still fine. I know some of you actually have plans on spring break, but we, like I said, we've been pushing very hard, and I wanted to give that opportunity to you. And if you want to wait till next week or even the Monday following, we can do that. We're still going to be on schedule, but give you a little bit of a break. Also, tomorrow I will be here in the morning through probably 11 to 11:30, but I've got a funeral to go to get to, so I'll need to be leaving campus about 11 or 11:30. So if you plan on taking the test tomorrow, it'll be in the testing center. So go ahead and, again, schedule that today. Go in and say, hey, I want to take it tomorrow at 11:30 or 8:30 or 2:30, whatever time. Of course, Cade, you'll have practice tomorrow afternoon, I'm sure.
Yeah.
As with this chapter, as you see, it is long problems. It may only take you an hour to take it, but it may take you 2 to 3 hours. So make sure you schedule enough time when you take it that you're not rushed. Monday, March 20th, we will start the next unit, but if you miss class, it'll be set up online so you can at least look at it. But what to expect, I'm going to try to get that done either today or tomorrow morning, get the schedule set up for the week after spring break. So if you do want to kind of work ahead during spring break, if you get bored, you can start on the week after spring break. So, okay, let's get to the review for the test. The first chapter from the Think Well material, the first concept we looked at was the improper integrals, and that was either an integration going to infinity, or, well, that's probably the easier one. something like that, where technically you really should turn it into a limit as b approaches infinity, and then you have the definite integral from 1 to b. So how would you do that? Integral of 1 over x is?
-1. My bad. I thought I was gonna -1.
So,
I'm glad.
working, I mean, again, a lot of terminology and notation to keep straight, but we'd have the natural log of b minus the natural log of 1. And, well, natural log of 1 is 0, so natural log of b as b approaches infinity would be what?
0?
Mm,
Oh, negative.
50-50
yeah, 50. Natural log of infinity, as x gets bigger and bigger and bigger, the natural log still gets bigger and bigger and
The natural log of
bigger.
0 will be negative infinity, right?
Natural log of 0, natural log as x approaches 0 would be negative
Yeah, negative.
infinity. Yeah. But the natural log as x approaches infinity would be infinity. So we would say this improper integral diverges. Now, if it actually equals something where the limit exists, then we would say what? Okay, it converges, and we can say converges to that number. Okay, so that's the improper integrals, one form of it. The other form, why would this be an improper integral? Okay, the denominator cannot equal 0. Well, the interval that we're going over includes 0. So technically, the way we would have to set this up, we have to separate it -1 to, well, even -1 to 0 plus 0 to 1. We'd still then need to change it to the limits.
Can you times 2 that?
Oh,
no.
No. It's not.
Symmetric?
It's not symmetric about the y-axis. If it would be, then we could go from 0 to 1 and multiply by 2. But this one would be approaching 0 from the left as we go from -1 to b. And then the other one, I always go the bottom integral limit, I let a, whatever letter you want to use, it doesn't really matter, but we'll say this one's the limit as a approaches 0 from the right this time, and then we'd have a to 1. So those are a little bit trickier to recognize why it's an improper integral, but keep that in mind. Anywhere the denominator, or anywhere the function does not exist, then you have to kind of chop the integral up into the two pieces and work from there. So again, could be improper integral diverges, or even in this case could be converges. And if it converges, find what it converges to. I think that's kind of the instructions I have. Find whether it's divergent or convergent. If it converges, what does it converge to? So. Okay, questions on those? Now with these, probably about one or two of these. Some of the application problems, there's only going to be one of. Obviously, we've got 10 problems, and we had 8 worksheets. 8 worksheets.
So it'll be 2 of each?
Or no, we didn't do 7.1. We did 8.8, and then 7.2, 7.3, 4, 5, and 6, and 7.
So we have
So 7 worksheets.
Yes.
Yeah.
Yeah. 1, 2.
Okay, then we looked at the volume, finding the volume of a 3-dimensional object, taking a 2-dimensional graph and revolving it either about the x-axis, y-axis, line y equals 1, line x equals 7, y equals -4, something like that. So we looked at a couple different techniques on this as well. What we call the disk method, and that would be, I'm not going to go through the entire problem, but at least give you an idea. Let's say there's our region and we revolve it about the y-axis. Disk method, we'll slice it and we get a disk, a cylinder, and the formula for that, formula for the volume of a cylinder, pi r squared h. Well, the h in this case we can represent as delta y, and well, in the integral that'll turn into the dy. Disk method, the bulk of it is figuring out what r would represent. Now in this case, r, the radius of that disk is going to be whatever x is represented by. Now we're not going to use x because we need everything in terms of y, but that'll be from this equation, and that might be something as simple as y equals x squared. Probably won't be that simple on the test, but well, it may be. I doubt it, but you guys know my test, so probably not.
Are you gonna let us know which one to use? Like,
No, I will just say find the volume of this region revolved about this line, and you can decide, do you want to use the disk, do you want to use the shell? Some problems will be easier using the disk, some problems will be easier using the shell. I think you can use either technique for those problems, and that this is probably one of those topics where they have at least 2, if not 3, since this is covering 2 different worksheets, disk method and shell method. We spent quite a bit of time on these, but for the radius being x, we'd have to change our equation, x equaling the square root of y, and so the radius would be in terms of y. And then we'd be going from here up to whatever this value is. I'll just put a for now, and pi times radius squared dy, and there's your volume. So I may actually throw you one somewhat similar to this, just to see if you can do a basic one. But you can bet that there's going to be some harder ones there. Now, maybe it's that same region, but revolved about the x-axis. Now, doing that, okay. Now, you could still use the disk, but what would we have? We're going to have a hole in the middle. That's going to be your washer. So you could use that. Like I said, I'm not going to say use the disk or use the shell. I'm just going to say find the volume. This one may actually be easier to use the shell method. Or this one wouldn't be all that bad using the disk, because it would be in terms of x. So, but if you would use the disk or the washer, you'd actually have, no, 2 parts to look at. Okay, remember it's the pi times the outside radius minus pi times the inside radius. And, well, as we used up here, we didn't say the y value was a particular number. We just called it a. Technically, the big, or the outside radius would be just the a. So we'd have pi times that constant squared minus pi times, well, this time the inside radius would be the y value, which, if that is the region we described, we need it in terms of x, so radius would be x squared, and then we square it. And we would be going from 0 to, well, whatever this would be. Let's see, if we're calling this a, y equals a, so x would be the square root of a. So now, definitely I'll be a little more specific than just throwing you a out there, but so there's the disk method. Couple different ways of using the disk method. The washer, okay, or the disk method with the hole in the middle. Remember, you got to subtract out the hole. Any questions about that piece of it? Now the shell method works nicely if it would be maybe something like this, revolved about the y-axis. And, well, we'll actually, let's just do A for that one. Now, revolving that about the y-axis, again, if you wanted to, you could do the disk. It'd be a horizontal disk. Everything would be needed in terms of y, but it would be possible. It would be so much easier, though, to use your shell. Okay. And the shell, 2 pi RH, and then times the thickness. Okay. If we do the shell, then we'd have the delta x for the thickness of the shell. Radius in this case would be what?
Will be A?
No. No. Radius is just the x value.
Oh, yeah.
We can have different sizes of the shell. The radius is,
where you cut it.
yeah,
Where you take the slice.
the radius of the shell as you move out, the radius gets bigger, but that radius is going to be whatever the x value is on our slice. Now, we need everything in terms of x, so r is just x. And we leave it as x. What would the height be, though? Okay, the height is going to be the y value, which in this case is the equation. So integrating the volume of this one, we integrate from 0 to a, whatever our outside part of that is, 2 pi times r times h dx, and then of course again it's probably not going to be quite that simple, but the idea is the same. make you think a little bit more than that. So, questions there? Next, we found arc length, and, well, some curve from some number to some other number. The length of that curve, well, this is that fun, had lots of fun algebra on this, right? Arc length, we go from A to B, and then in this case we can say from x equal A to x equal B. Now remember, on arc length we never had to go dy. We could have, but we never had to, because technically arc length is ds, and we represented ds as square root of 1 plus the derivative of y with respect to x, quantity squared. So however the curve is set up, we can use ds, we can turn it into dx no matter what. Okay. And the biggest problem with this one, well, once you found dy by dx and plugged it in here, squared it, then added the 1, there was a lot of algebra and a little tricky thing of recognizing sometimes our 1 plus y prime squared turned into the square of a binomial, and
which turns out being the opposite.
Okay, the square root of the square, they cancel out and you're left with whatever this was. Of course, it's much more complicated than just a plus b, but yeah, that some of the functions, to make it turn out nice, to make it turn into something we can factor, the original function looked really ugly. Lots of fractions in there and lots of manipulation, but it was doable. Just the biggest problem on these are definitely the algebra that goes along with it. So
I have a question.
Yep.
Is it always going to be 1 plus?
Arc length will always be 1 plus whatever that is, the square of the derivative. So,
are you going to do the surface area of the arc length as well?
yes. We then kind of stepped it up one more notch to surface area, and that would be if we took an arc length here, revolved it about, well, whether it's about the x-axis or the y-axis really doesn't matter. It'll change slightly what the radius will turn out to be. But let's say we revolve it about the y-axis. We get that for our surface. Surface area, we take a slice. Well, that's going to be the circumference. Essentially, take a slice, we'll have a ring. You can essentially cut the ring and lay it out flat, and you have a rectangle. Well, the length of that rectangle is the circumference of your ring. So 2 pi r, and then the tricky part thinking about that is the width of that rectangle is not necessarily delta y or delta x, but think delta s, your arc length that we just did up here. So 2 pi r ds would be the general way we write the formula. And again, we could still go from A to B, even though this is x equals A to x equals B, ds would be precisely this in terms of x. Now, R is the thing we have to keep track of. The R in this case, radius, I guess there's our slice, radius of our slice, is the radius represented by X or Y?
X.
Okay, and since we need it in terms of X, we just put R equals X in there. And then times ds that would be the surface area of something revolved about the y-axis. How does that change if we revolve it about the x-axis? I don't think I have a... Yeah. Real rough here.
So it
But
would be 2 pi.
what's the radius this time?
Will be y.
Okay, the radius is going to be y this time. Now y will be whatever the equation is for the curve. So maybe that's y equals x cubed, whatever the formula was.
So then it'll be the cube root of y.
If you need it in terms of y,
Okay.
but surface area, we can keep it in terms of x because of the ds. We always turn ds into terms of x. So we could still say integrating from a to b. Again, this curve here, the only difference would be revolving it that way. So 2 pi y, which is whatever the function would be, in this case x cubed, times this same thing.
Like on the radius on the first one is equal. Wouldn't it be like equal the function?
We don't need to equal the function because the radius is the horizontal radius, which represents the x value.
Okay.
And since we're using ds in terms of x, we don't need to use the equation of the curve, we just need x. Okay, we don't need to turn it into, like you said earlier, cube root of y, because we need it in terms of x. Whichever way we go, we can always keep it in terms of x. It's just, is the radius represented by x or is the radius represented by y? If it is y, what is y in terms of x? Okay, so arc length, surface area, a little extension there. Yeah.
So those are like formulas, those work every time.
Correct. These will be your arc surface area formulas, whether we revolve about the y-axis or revolve about the x-axis. Okay. I don't think I revolved anything about anything else, so those are the only two. Now, arc length, well, no. The volume, we may revolve about something else than the x-axis or the y-axis. But like I said earlier, x equal 3 or y equal 25, or, well, maybe not quite that big. But okay. And that was 7.4 worksheet. So next, 7.5, we calculated the work done in different situations. Work is very simply the force times the distance traveled. A lot of that force was the weight of something, and then distance, maybe we're emptying a tank, pumping water out of the top of a tank or something like that. So force would be the weight, and D would be your distance traveled. Now, the first part of that section and what the Think Well material talked about was the springs. So don't forget about those as well. Hooke's law says the force is proportional to the distance stretched or compressed, which turns into forces kx, and you'll be given enough information at the beginning to find k and then go to your integral and what's the work done in stretching a spring 10 inches. So integrate from 0 to 10 and calculate, find out what the proportionality constant is based on the given information. Work done in propelling something into space, that force is inversely proportional to the square of the distance. So that force would be k over x squared. And make sure you have these on your notes.
And the radius will be around 4,000.
Yeah, the radius of the Earth, I would give that to you. But yeah, that's radius of the Earth was what, 4,000 miles? I think that's some information I would give you. And then, yeah, the pumping, what's the work in pumping water out of a tank? Those kind of slightly different. In that case, the force would be the weight density times volume. And weight density, again, I would give you that either 62.4 pounds per cubic foot, or what's the 9,800
Yeah.
That's okay.
newtons per cubic meter. And I will give you that if that's necessary. So, questions on the work? Okay, then center of mass, or center of gravity. At the 7.6, find what we call X bar and Y bar. And for that, you'll need your formulas. X bar, well, the denominator is the total mass of the region we're talking about, and that would be, well, density times area. It's almost as simple as find the area of your region, which you did back in Calc2. Hopefully you remember that. But usually, if it's a region between two curves, it would be that, and then times the density. They use a Greek letter usually to represent density, but the nice thing about the center of mass, the density doesn't matter because it shows up top as well. And if it's a constant density, the densities cancel out. So it's a lot easier to work with. And then your numerator is x times f of x minus g of x. So that's how to find x bar, the x coordinate of the center of mass. Now, y bar, we could do something similar to this, but we'd have to make these in terms of y. there's a nice little formula, I think he mentions that. The denominator is still going to be the area of the region, but the numerator is going to be 1/2, and we're going to keep this in terms of x, even if it's y bar, but 1/2 times f of x quantity squared minus g of x quantity squared. So given those two formulas, again, it's almost like finding the area between two curves, but manipulating the formulas slightly to find, well, the numerator is actually considered the moment, the tendency for it to rotate about x-axis or y-axis. We don't get into that too much here in Calc 2, but next year in statics we'll get into that a lot. So, okay, questions there? That one, that problem, it's a lot of work, especially you are essentially calculating 3 different integrals. The denominator's the same for both parts, but then the numerator changes for both parts. So, okay. And finally, what we talked about yesterday, the fluid force. And that's on the 7.7 worksheet. And fluid force, the force is equal to the pressure times the area. Well, the pressure is the weight density times the depth, and then so times the area. So anything, say we have a circular window in a submarine and it's submerged 100 feet, well, the center of the circle, we'll make that the center, 100 feet under the ocean depth. Well, what we have to do, take a slice, whatever slice, and figure out, well, the weight density, water, again, either the 62.4 pounds per cubic foot or 9,800 newtons per cubic meter. That's what the W is. The depth, well, the depth that this would be under this much water, we can call that the Y value. So depth would be the 100 minus Y. And then the tricky part in some of these turn out to be the area. The area of that slice, well, it's just a rectangle, but the width of that rectangle would be delta Y. So it's really, tricky part is finding the length of that rectangle. And because of symmetry here, we'd have, well, this x value to this x value, because of symmetry, this length would be the same as this length. So we could say the length would be 2 times x sub 2, or just 2x. Once in a while we can get by with because of the symmetry. But what we have to do is figure out what x represents, and that's going to be based on what object we're dealing with. In this case, a circle. There I go with that a again. X squared plus y squared equals whatever the radius is squared. So x would be square root of a squared minus y squared. And then 2 times that square root. So fluid force, integrate from, not 0, we're integrating from negative a to positive a, and then the weight density times the depth times 2x, which we just calculated as square root of a squared minus y squared,
What is it, 0?
and then dy. No, here would be 0. The circle, again, sometimes it will be from 0 to the top of the figure, but in this case, circle is slightly different. Go from the bottom to the top would be negative a to positive a. And we do not have symmetry there because the pressure down here is more than the pressure up here. So don't try to just go from 0 to a and multiply by 2. That works for area, but not for fluid force. So, okay. So there's our last type of problem. And any questions on that?
So the width, I mean,